Right, so right off from the bat, I'm going to do two things. One, I'm going to commit a heresy, and two, I'm going to say something incredibly foolish. So, heresy first. The best fuel we know of are hydrocarbons, petrol. Petrol has an energy density of something like 12 kilowatt hours per kilo. And even if you burn it in an engine and get only 30% of that back, it's still 4 kilowatt hours per kilo. The top of the range lithium battery is something like 250 watt hours per kilo. So we're talking about orders of magnitude in difference of what energy is stored in these two different devices. So there currently is none better than petrol. So if somebody wants to throw a rope over a beam and hang me for that one, please wait a second. The second thing I'm going to say is foolish. We can pull that petrol straight from the air. And that sounds ridiculous. However, it's actually not that ridiculous. There's a whole bunch of compounds that are catalytic for the production of something called syngas. Syngas is a mixture of hydrogen and carbon monoxide. When you put water and carbon dioxide together, and you pump those over these catalysts, they will produce syngas. One of the catalysts is this stuff, cerium oxide. It's actually better known as jeweler's rouge. It's used for polishing stones and jewellery, that kind of thing. And that's pretty much where it stood for many years, making optical instruments for telescopes. Despite it being a rare earth element, and it's a rare earth element because it's the second in the lanthanide series on the periodic table, it's not that rare. It's about 66 parts per million in the Earth's crust. And okay, that doesn't sound like a lot, but copper is only 68 parts per million. So it's actually just behind copper in terms of abundance. And some of the more popular metals, if you like lead for instance, is 13 parts per million, and tin is 2.1 parts per million. So in that ranking, despite being called a rare earth, cerium is not particularly rare. This stuff is catalytic for the production of syngas. If I take a lump of this, press it together, now I do have to heat it up to quite high temperatures, I believe it's about 1300 degrees Kelvin, then pour carbon dioxide and water over it, syngas will come off. And that's actually quite amazing if you think about it, because it has such potential. And of course, that potential has been known about for a very long time, and there's about 30 years of research on this. Now, being able to produce syngas directly from the air doesn't sound like such a great thing really, but syngas is also well known for the catalytic conversion using cobalt into a whole range of things, including ethanol, methanol, kerosene, and everyday petroleum. It can be done. That's the whole point of this. There are two processes involved. Those two processes can produce petrol, kerosene, which is jet fuel, straight from carbon dioxide and water. So, if we get a bank of scrubbers and we stick it outside and we suck in all the air and take out the carbon dioxide and take out the moisture, we have our raw materials. If we can then pump that mixture into a chamber that we can heat that high, they will produce syngas. That syngas can then be pumped into another catalytic container with cobalt in it, and you will drip jet fuel out of there. Now, that's actually almost magical. It really is, and it does sound like a nonsense when you first say it, but as I say, it's such an interesting area of research to people. There's 30 years of work. Now, one of the issues, obviously, is this is a rare earth, but it works actually with a surprising number of things. So it'll work with zinc oxide. And there's so much zinc oxide, we put it in suntan cream. It'll work with iron oxide as well, and of course it works with this stuff. This stuff is also used in fuel cells, so it's got a bit of competition for some of the new technologies on what this can do, and they use it in fuel cells. But any of those materials will do. Now, I do have a love of open access research papers. I love them because everybody can access them. You just go to the right place and you can read that research paper. And here is an open access research paper going into the ins and outs of syngas production using various methodologies and using various
chemicals as catalysts for doing exactly that, and you'll notice zinc oxide, iron oxide and cerium oxide on that list. So that technology to take the CO2 and the water out of the air, heat it and produce syngas is actually relatively well known. Now it has been taken up by the Swiss of all people, because most of this stuff, it just sits in a research lab because it's, an oddity more than anything. But the Swiss have worked on this and actually created a system beyond the research lab. Their system is now at full scale. It's using 15 kilowatts of solar energy in a 16-inch window with a tower-mounted solar reactor. And in that reactor, you have a packed bed of the cerium oxide that you're flowing those two gases out over. And as I said, those two gases are being taken out of the air via scrubbers and purified. And they concentrate the solar so that it's approximately 2,500 to 4,000 suns being hit there, hitting it at around about 1,500 degrees centigrade. And that's hot enough that the cerium oxide can act as a catalyst to split that water vapor and CO2, carbon dioxide into carbon monoxide, hydrogen, and produce the syngas. That syngas is then fed in this system to produce kerosene, which is pure enough apparently to be able to be used as jet fuel. So the Swiss are taking it one step further and taking it from that lab bench to actually quite a large-scale trial looking at producing jet fuel straight from the air. Now, I find that fascinating. But of course, there are issues with it. There are always issues with everything. It's actually only about 4% efficient, which is a pretty low efficiency. Now, the researchers reckon that they can get that to 20% efficient, which is actually kind of quite impressive when you think about it. And of course, the benefit is, if you burn it like you burn a normal hydrocarbon, then of course it puts CO2 straight back into the air. But as you're pulling the CO2 out of the air in order to do this and using sunlight to do it, then of course it is net carbon neutral. And that appeals greatly because we have a huge industry, a huge infrastructure involved in the burning of hydrocarbons. If we have to abandon that, the cost is incredible. And of course, at the end of the day, it's us who bears the cost. Now, if you can sidestep that cost issue and continue to use those hydrocarbons, then we can have a net negative impact very quickly indeed without having to make the massive spend on the infrastructure change, which is probably one of the things that's holding everybody back so much, because that spend is enormous. And so there's a great deal of hope for the direct production of petroleum out of the air. It is a very active research field. As I say, I pulled up one open source paper for you to have a look at. It is a 30-year-old industry with a ton of research going into that two-step process. One, the creation of the syngas. Two, the modification of the syngas into petroleum. If you go to Google Scholar and put those in, you'll find a huge list of papers on it that you can read and find out what's actually going on. But this result from the Swiss trial was released earlier this week, and it is very promising indeed. Yes, there's a few years to go before it actually gets to that 20%, but it's quite exciting to know that they're actually working on it. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.